step 3 of prismatic beam design. It requires the maximum shear stress theory, and as I continue for the worksheet 14D, we go over the apply of the failure theory, which is the maximum shear stress theory that we just talking about. So apply failure theory. So in this case, according to the maximum shear stress theory for step 3 for the beam design, as we mentioned earlier, according to maximum shear stress theory, for ductile material, what are ductile materials, what are the brittle material, go to lesson 3, material properties. You will review that. Then we have a few scenarios here. If you find out sigma 1, sigma 2 of so principal stresses, sigma 1 and sigma 2 from the Mohr circle or equation, sigma 1, sigma 2 have the same sign, and they both have the same sign. So either positive or negative, same size. Then how to check for the maximum shear stress theory? We have to check both the absolute of sigma 1 have to be less than the sigma allowable, and sigma 2 absolute number have to be less than sigma allowable. And if they have an opposite side, if sigma 1 and sigma 2 have opposite side, then what we do? We have one criteria, absolute of the difference sigma 1 minus sigma 2 have to be less than sigma allowable, and that needed for worksheet 14D in step 3 we have for this. Okay, so that shear stress theory, when we check for the maximum combination of shear and moment, and when you have combination of shear moment, you have both sigma x and tau xy, you need to find out the principal stresses. In this case, sigma 1, sigma 2, that go back to our stress transformation class lesson, and then from that we can be able to check with the criteria just shown here for the maximum shear stress theory. The last lesson that I want to emphasize here is sometimes you check the tau in step 2, which is the maximum transverse shear stress. Check for that. What are the equations we have? Just want to review here. So we checking tau, the transverse shear stress in beam design, which is the step 2. Yeah, and this is the last note we have. So for general case, and for this class, I emphasize that we should apply for general case. So whatever happened, it apply for all kind of beams, whether it standard shape or rectangular, etc. So for this class, I also emphasize here, this class we use it. If you do the study guide, let's talk in here, this class. So use this for this class, okay? It here. So all the case, we have tau max equal to the shear max times Q at the neutral axis over IT. VQ over IT, if you recall that. So the maximum of the V. And for the rectangular beam, what is tau max for rectangular beams? What do we have? The tau max, believe it or not, from the VQ over IT, it will be 3 over 2 V max over the area of the cross section. How is that? If you have, I just go very quick in here. If we have a cross section which is rectangles, and we have the neutral axis here. You see neutral axis, as everyone know, and the thickness, the width is B, and the height is H. You have that. And for Q, from the neutral axis, so we draw that here, half of that rectangles. This is the neutral axis. So the distance here is still B, as you can see. The distance should be, and the height here is h over 2. So from this equation we can have Q for NA is equal to the area BH over 2 times the distance from the neutral axis to the centroid, h over 4. So we can be able to find out that is BH square over 8. B square over 8. And we also remember for I, X for this rectangle equal to parallel perpendicular cube over 2 over 12. So you have B, the whole cross section, we have BH cube over 12. So these two to plug in here, it will be equal to 3 over 2 V max A, where A equal to, and you can see A actually equal to BH, because that rectangle, the width times the height or the depth of the beam. So where that equation come from. And then for the approximate, to determine approximate at the for the standard shape Y flange and the American standard, so for Y flange and S beam, which is Y flange shape and American standard. Normally, a most complicated one is that we did in step 2 earlier in problem 14D that I will show you. But in the real life, you can do a simple equation which is more conservative. The tau max, we only consider the web will carry the internal shear force, not the flange. So with that, more conservative, we just ignore the shear that carry due to the flange. We also have the V max over the area of the web. And that, how to determine the depth of the web, it can be equal to that one, the area, so it will be depth, the depth time the thickness of the web, and which is available in Appendix C. So with that, we're done for this class here. And again, go back to worksheet 14D to apply on objects to the design of the beam, prismatic beam. And keep in mind, for the step 2 in this class, we use T max VQ over ITs.